Hello, this is Dr. John Hockery at Millersville University. Today we're going to talk about solid state switches as they relate to power conversion and control in industrial scenarios. So we've talked about mechanical switches, and so the comparison here is that solid state switches have no moving parts. They're going to allow us to sense the physical world around us, but without having a mechanical opening, closing of a mechanical contact. And there's going to be benefits to that in the longevity and in the type of sensing technologies that we can use. And so we're going to talk about temperature, pressure, flow, photoconductive, proximity, magnetic, and ultrasonic. And so if we look at temperature first, we typically measure temperature electronically by measuring a difference in resistance of an element. And this type of an element is termed a thermistor. So it's a thermal resistor. It's a resistor that changes its resistance drastically with changes in temperature. Most materials do this, but a thermistor has unique properties where the change in resistance is significant with small changes in temperature. And this allows us then to use an electronic circuit to measure differences in resistance and then correlate those to differences in temperature. So the way this works, a thermistor, if we apply a voltage across it, and we then can have a voltage drop that correlates with that resistance. And so as the temperature changes and the resistance changes, the voltage drop across the resistor or thermistor will change. We then use that voltage to drive or control a solid state relay. And we're going to talk about those in more detail later. But a solid state relay functions very similar as a mechanical relay, except that there's no coil with electromagnetic forces that are produced, but there are transistors. And so when I apply a voltage to the transistor, it energizes, quote unquote, the transistor, allowing the output to conduct or not conduct, or to be open or closed, kind of in the mechanical relay terminology. And so a temperature thermistor is just going to drive or control the coil or the input of our solid state relay that then determines if the output is either open or closed, that then actually controls the device or the load that we're considering. And so thermistors typically are in two different types. They have either a positive temperature coefficient or a negative temperature coefficient, meaning a positive temperature coefficient, an increase in temperature results an increase in temperature along the x-axis results in an increase in resistance along the y-axis. And that's fairly typical for thermistors. I can have the opposite effect. I can have, as I increase temperature, I can decrease resistance. That's just a reverse or negative temperature coefficient. But every thermistor has properties of its element that allow it to change its resistance as temperature changes. And then we can use that along with the voltage drop across that thermistor to understand the temperature. And then we drive that voltage drop, can power a transistor that then ultimately opens and closes a circuit in the same way a mechanical relay does. So temperature transmitters or sensors are a very common solid state switch that we use. Another common one we'll get to is pressure. And pressure works in a similar way. The one difference in a pressure is there's actually a mechanical pushing or pressing up on a diaphragm. And seated next to that diaphragm is a strain gauge. So a strain gauge is a very sensitive device that changes its resistance based on pressure. Specifically, there's a Wheatstone bridge that is kind of in that strain gauge, and it has an arrangement of resistors as we see in the top right. And there's an equilibrium or a balancing of resistance between the positive and the negative points here. And I can have then an overall or output voltage. As I push or pull on that strain gauge, one of the resistors will actually be flexing and it will change its resistance. And so the balance, the total balance of resistance will change, thus changing the voltage. And this is susceptible to very slight changes in resistance, so very minute changes. And so this is a typical arrangement that we use in a strain gauge. to then drive this voltage output controls or drives a solid state relay that then has an output that then gives us a signal or a contact that controls the load. So again, in a pressure transmitter, that's a solid state. We're using a strain gauge in conjunction with a solid state relay internally. And so no moving parts save the diaphragm. So there's the liquid or fluid that's pressing up against, but the circuitry has no moving parts. And that's the key distinction for this slide deck in solid state being no moving electrical parts. For a flow sensor, we're also going to use a resistive element. And we can have a situation where we have this resistor, and as we apply voltage and flow current through it, it will heat up to a known temperature based on that voltage. And if I flow liquid past that probe, it will actually suck away or pull away that heat off of that probe and cause it to appear to be colder. Okay, with no flow, there's no escaping or pulling away of the heat, and it just stays there kind of stagnant. And I can use that change then in temperature and then resistance and ultimately voltage, like we saw on the thermistor slide, to then drive a solid state switch, just like we previously seen. So this is the same type of thing that happens on a windy day when you put your finger in the air and it feels different than if you lick your finger and put your finger in the air wet. Okay, so when something is wet, it feels colder because that air is blowing across, sucking off that temperature. Or if the wind is not blowing, you don't feel colder because there's no wind pulling your thermal heat off of your body. We typically use this type of flow sensor in settings where we have tubing and we have a flow of liquid through the tube, whether that's water, oil, gas, you name it. And we may have, the sensor physically, seated in the tube, and it will be driving an alarm. And this flow sensor symbol here, we have, looks like a switch with a little vane, like a weather vane hanging down off of it. The weather vane piece is illustrating that flow or flapper action that's going to happen. The diamond that we see around the entire symbol is indicating solid state. And so that's the case for any of the sensors we're talking about in this slide deck being solid state. Whenever we put a diamond around the symbol, that's telling us that it's a solid state device, no moving parts. And so we can use the typical kind of limit switch style symbol, attach on kind of this vane or flapper hanging off the bottom. And then, of course, we can put a diamond around it to indicate it's solid state. And if it's touching, then we're saying it's normally closed. If we want it to be a normally open configuration, we would draw it not touching. And that would be the case too with our pressure. We show the kind of a diamond around that symbol, that symbology as well. So moving on to the photoconductive sensors. These use also resistive elements that change resistance with changes in light. So just like you can change the resistance based on a change in temperature, you can change the resistance of some type of materials with a change in the light being applied to them. So a really common application is a photoconductor looking at a pilot light to make sure that it's still burning as I'm applying gas or not gas. Pilot lights are very important. They will burn off any leaking gas before it becomes too much and causes an explosion when the burner is turned on again. Okay, so a pilot light is actually a safety device as well. And so we want that photoconductor to be confirming that that pilot light is always lit. Otherwise, we need to sound an alarm. In the circuitry diagram on the right here, we're applying it to a photocell in a traffic, or a street light. Same concept. As the changing resistance, right, will result in a changing voltage, which will then apply a voltage to a solid state relay, which has transistors in it, that then has an output contact. right? And so just like we've talked about with the temperature sensors and the pressure sensors, this photoconductive is using the same properties of a change in resistance caused by a change in light that's then producing a changed voltage drop that is being applied to a solid state relay to energize or de-energize that solid state relay, causing the contacts to open or close. Again, no moving parts, just using a change in light to drive that solid state relay internally. The testing of all of these devices is similar, whether it's light or temperature or pressure. You would use a DMM on the resistance function, and you'd measure the resistance across that element, and you would apply full light or apply no light, and you're hoping to see a change in resistance, right? Or you apply full temperature or no temperature, depending on whatever physical phenomenon the sensor is looking to sense. That's what you're going to give in the extremes to see, do I see a change in resistance when I see an extreme change in light or temperature? And that's how we can troubleshoot whether the resistance is actually changing. If we see no change in resistance between no light versus extreme light, then we can assume that the photoconductive element is not functioning properly. And that's when we go pull out a new one. Another photoconductor would use LEDs or a light emitting diode. And so we have a situation where, from a diode perspective of a positive anode and a negative cathode element combination, that as light is applied to that element, it allows conductivity across the diode, and that then allows current flow. And so we oftentimes use this in laser-based sensors where we have a laser beam across a conveyor belt, and once the laser beam is broken, it knows to fill the box with packing material. Typically, this has an amplifier circuit that's beyond this class, but it's not going to have any moving parts, right? The key point for us here is we're using diodes and semiconductors in our circuitry of our sensors so that we're not using mechanical contacts with coils. We also have proximity sensors. So those are sensors that allow us to sense iron-based and non-iron-based materials without touching them. And so for an inductive proximity sensor, we have a circuit where we turn on an oscillator circuit internally. So we turn on a circuit that produces, magnetic lines of flux in an oscillating fashion. Okay, so it's emanating magnetic forces out from beyond the barrel end of the sensor. And if I bring in a piece of metal, okay, close enough into that magnetic field, it will change the shape or change the intensity of that magnetic field. That will then be sensed in the oscillator circuit as a change in how much current flow is happening and producing the magnetic field. So as the magnetic field changes, the electrical circuit will have some change in it. It'll be reflected back in, and we will see that then as, hey, something changed. So now drive a transistor-based solid-state relay to open or close a contact. And so for an inductive proximity sensor, we're using magnetic inductance. And so we need ferrous iron-based materials to be sensed. And so I can't sense typically a non-metallic material, but I can sense a metallic material, which is great for a lot of machines. You want to know, like when I home the CNC machine and it rotates all the way back to the one end, there's a piece of metal it's going to get close to, and I'm just going to know I'm at the close to the metal, so stop moving. There are capacitive proximity sensors that work similarly, but use the capacitive effect. And so whenever we put two conductors next to each other, the closer they get, the more conductance they produce. The further apart they are, the less conductance they produce. And so I can have a sensor that the barrel end of the sensor is the one conductor plate of the capacitor, and then whatever the thing is that I'm sensing becomes the other side of the capacitor. And if that thing is close enough, it produces enough capacitive buildup charge that it is sensed by that internal circuitry that then drives the solid state relay to drive the contact output. Okay. So on the capacitive sensor, you're using the charging a capacitor by making that thing you're sensing get close enough that it becomes part of the capacitor circuit and produces a charge that can be sensed, a voltage that can be sensed. So I can have non-metallic things all of a sudden now that I can sense. There are dielectric constants that every piece of material typically exhibits. Carbon dioxide typically has a dielectric constant of close to 1. But anything above 1.2 is typically a high enough constant that there's a big enough difference that enough charge will be produced or voltage will be charged that I can sense that. And so these are the types of materials that have that higher than 1.2. And so all of these things, especially when we use these materials in our manufacturing processes, I can all of a sudden sense whether they're there or not by using a capacitive proximity sensor. So the proximity sensors are non-contact. Okay, so they're without touching, you can sense it, whether you're using magnetism with the inductive or capacitance with the capacitive. The next one is specifically a magnetic sensor, and more specifically a Hall effect sensor. And so a Hall effect generator is a type of device that has a quartz substrate, so a thin piece of semiconductor, usually quartz. And if I run current laterally through the quartz, a voltage will be produced perpendicular the other way, right? So current is running kind of left to right, kind of down, top to bottom, left to right. Then I will have a voltage in a 90-degree perpendicular to that I can measure across that substrate. And that's just the phenomena of nature, right? Called the Hall effect. As I bring a magnet within a certain proximity of that substrate, I will get a change in voltage. Okay. And if the magnetic field is strong enough or the magnet is close enough to the Hall effect sensor, then I will see a high enough voltage to say, hey, something is there. Something magnetic is close enough. I see that. And of course, I can use that voltage to drive a solid state relay. So the input or the quote unquote coil part of a solid state relay to turn it on or energize it to then change the contact output on that solid state relay. So Hall effect sensors are a very common sensor that we use by seeing or not seeing a magnetic field. And I can either bring the magnet straight down axially, and I have to get within some distance. And typically it's a very small, 1/8 of an inch or less distance. Or I can come laterally across, right? I just have to get it within, that target area within a close enough distance. Okay, so I can do, sliding across or coming down at it. The applications for these types of sensors are a myriad. So whenever I want to spin a shaft and measure the rotations of that shaft, I typically use a Hall effect sensor. So I put a sensor close to the shaft, and on the other side of the shaft, I have a magnet, and I just measure how many times I see that magnet. And if depending on how fast it's spinning and the diameter, I can figure out the speed. And I can have one piece that it's sensing, or I can have multiple pieces, right? And get a higher precision or see different angles of rotation. Okay, so do I get one blip every rotation, or do I get 100 blips per rotation? And I can decide, and I can have different sensors for those different applications. Another one is a joystick. And so newer style joysticks actually have this Hall effect sensors kind of distributed around, divided out by so many degrees. And of course, the more sensors you have cutting up that 360 degrees, the more precise location you can get on that joystick. And then there's a magnet kind of ring. And as you go and move that joystick closer or away from the different magnets on the different degrees around that circle, you understand where it is. That's a pretty fine, pretty precise way to understand a joystick action. Another way is instead of spinning, well, you can spin with like a teeth, almost like a gear, and there's gaps in the gear. And when you have the gap, you may measure it. And when you don't have the gap, you're shrouding the magnetic lines of force, and so you don't see it. So you get this sees, no, doesn't see, yes, no, see, no, see, no, see, right? And you can start counting, how many per revolution or per time. You could also make this flat or straight linear. And so you could be moving linearly back and forth, and you could be measuring, how fast you're moving based on how many ticks you see in a certain amount of time. You can put these sensors on a conveyor belt. So you can use this style shaft speed sensing and can apply it to a conveyor belt to understand how fast the conveyor belt is moving. So if you have a box going down the belt at a certain speed and you need to pick it up with a robot, the robot needs to know how fast is that belt spinning. And so how fast do I need to track alongside the box when I pick it up? Probably the one that we've all used is a security card in like a door lock. As you put the card in, it has a magnetic card strip and it gets close enough and it says, oh, I'm here, read the security code on the card. And so that's using a Hall effect sensor. I can also use the Hall effect for liquid level. So as I'm raising or lowering this beige disc, when it gets to a certain point, it sees, or the magnetic Hall effect sensor sees the magnet and says, oh, the level is there. In a float level or sump pump pit, it's a similar type of configuration where that float level gets to a point where, boom, I'm close enough to this magnet and now I see it's there. So it's a go, no go. All of these are go, no goes. Similar to this rotating speed, I can apply it to, how much have I unrolled, right? So I'm not counting just speed, I'm counting like rate and how long. So I know at this certain rate, and I've been unrolling for 2 minutes, I can calculate how many feet I've unrolled. And so these are all very common applications for Hall effect sensors that use that magnetic Hall effect phenomena. Another type of sensor is an ultrasonic. And so these are like, BAT ultrasonic, where it sends out ultrasonic pulses that are received. And of course, non-contact, they're going to drive a solid state relay inside that's going to open or close a contact. So there's no moving parts, right? And I can either have two separate parts of the sensor, so a sender and a receiver, or a emitter and a receiver. That's called direct mode. I can also have a diffuse mode. This is how bats work, right? So their mouths send out the sound that bounces off of the object and comes back to their ears, right? And the length of time it takes to hear that echo back, you can calculate how far away something is. And that's how bats use echolocation, right? They do the chirps out and they're tracking how long it takes and in what direction the sound is bouncing back from. And so we have the ability all of a sudden to either say, I know when I see something within a certain distance, or I can see something within a range of distances. Oftentimes, when we talk about ultrasonics, there is an ability to do that analog, like everywhere between a range. And so, the distance away from something from the sensor will correlate to a voltage, right? And I can have a correlation that as the distance increases, the voltage increases. I can also say I don't care about anything past a certain distance. So oftentimes ultrasonic sensors, you can calibrate them to say if something is past half an inch, I don't even worry about that, or half a meter, or whatever the distance is. If it's farther than so many inches or meters, I don't care, right? So that's a way to suppress or block out something beyond a certain distance and only look at, things within this distance to where the sensor is. So those are applications of solid state sensors. They are designed and implemented around transistor solid state relays. And so the elements that are sensing the physical phenomena, temperature, flow, pressure, and such, are just energizing or not a transistor that has a contact on the output that is either open or closed. That's an oversimplification, but that's the comparison to a mechanical relay that will make sense with the other things that we've gone through in this class.